So just quickly thinking about what we talked about last time with heat capacity. When do we actually use it? Well, we use heat capacity anytime we're talking about a temperature change. So we see it anytime that we're looking at the inclines on our heating curve or cooling curve. So if you see an incline or a decline, some raise in temperature or lowering of temperature, that's when you're going to use it. So if you're in just a solid and you're heating up to where you can melt, or if you're a liquid and you're heating up to where you can boil, or if you're a gas and you're heating up beyond, that is okay. Those are the times that we can use it. But we have to know what state we're at. If we're at a solid or a liquid or a gas, there's different heat capacities. We have to know where on this chart we are. So for us, we really need to know that at 0 degrees Celsius, that's the melting and freezing point of ice for water. And at 100 degrees Celsius, that's the point of vaporization or condensation for water again. Now, different substances have different amounts, but those are the ones that we're going to have to know. And we have to think about this. If we're at a plateau, we can't use this because our delta T, so our change in temperature, is 0. Anytime that we do math with that 0, it's just going to end up as 0. And we know that there's energy. We know that we need energy to turn that solid into a liquid. We know we need energy to turn that liquid to a gas. Or the opposite way, we need to lose energy for a liquid to become a solid, and so forth. So we need something different when we get to those plateaus. So anytime that you see a plateau, we know that there's either melting or freezing or vaporizing or condensing happening. There's no change in temperature. So let's look at just that first section. That's what we call heat of fusion. That's where we're having our melting or our freezing. It's the lower plateau if you're looking at the full curve. For water, it's 334 joules per grams. Notice there's no temperature here because there's no temperature change happening. It's staying constant through that motion. Just like when we were melting our ice, when we made our own heating curve for water. And the upper one, so the upper plateau, that's our heat of vaporization. That's where water is going to either vaporize or condense. And it's 2,260 joules per gram. There's so much energy needed for that to happen. So these two, where there's no temperature change, we need a different system. We need either heat of fusion or we need heat of vaporization. So let's actually check out one of these problems and do it together. So suppose during a volleyball practice you lost 910 grams of water due to sweating. If all of this water evaporated, how much energy did the water absorb from your body? So what can I figure out already? These are given. So I'll give you the liquid H2O, right, heat capacity, the solid H2O heat capacity, the heat of fusion, the heat of vaporization, both for water as well. So what am I looking for? Well, I'm looking for how much energy. Notice how I underlined that as I read my problems. And I circled what I had. So I only have grams. I'm looking for how much energy, and I have a phase change. I'm reading this question and I'm noticing that it's talking about water evaporating, which means that it's going to vaporize. It's going from a liquid to a gas. So my graph should look like this. My time versus energy temperature graph, right? So it's going from a liquid to a gas. We're at a plateau. And if I look at it again from just a systems point of view, where we have our LOL chart, we have our temperature and temperature staying constant. We have a phase change. So I'm going to use that knowledge of that phase change. But now I have to pick the right one. I'm evaporating. I'm vaporizing. I'm going from a liquid to a gas. So that's that heat of vaporization. So I'm going to use this number. And I'm going to convert it the same way that I did with heat capacity. I'm going to put it out front with the unit that I want on top. I want to know how much energy, so that's going to be out front on top. And I put that over the gram, right? It's for every 2,260 joules, 1 gram either vaporizes or condenses. So I have 910, so we made sure those grams are going to cancel, right? They're opposites. One's on bottom, one's on top. And then we multiply. So 2,260 times 210 grams, and it equals this, 2,056,600 joules. And that's all that it is. So this is a really easier conversion than we did for heat capacity, right? We're not canceling out both of those units. But we really have to know where we are on this chart. What's happening to this liquid or this solid or this gas, or what's going on? So once we define what's going on, then we can start doing our math. Okay? So I hope everybody has a great day. And if you have any questions, just ask.